You are welcome to another video of the course IPv6. In this section we are going to compare IPv4 and IPv6 headers, which IPv4 header fields have been removed in IPv6, what new fields and capabilities have been added in IPv6, and which fields have been just renamed without any changes. We will also have a brief overview of IPv6 extension headers. This image illustrates the difference between 20-byte IPv4 header and 40-byte IPv6 header. Although the IPv6 address size, which is 16 byte, is 4 times larger than IPv4 address size, which is 4 bytes, the overall IPv6 header size is only twice as large as IPv4 header. This highlights the efficiency of IPv6 design, which optimizes header size even with expanded addressing capabilities. I'm not going to deep into details of IPv6 and IPv4 headers, but I will provide an overview of the key differences between them and explain how IPv6 header has been optimized. I've highlighted certain fields in headers using colored boxes. Red indicates fields that have been removed in IPv6. Blue shows fields that still exist but with a different name. And green highlights the new fields added in IPv6, and fields with no colored boxes, including version and source address and destination address, have the same name and function in both IPv4 and IPv6. Let's begin with header fields removed in red color, which have been removed and no longer exist in IPv6 header. We will start with header lengths. In IPv4, these fields indicate the header lengths because size of IPv4 header could vary due to options field. However, the options field is rarely used, but the IPv4 header size is variable by nature. In contrast, IPv6 header has a fixed length, making header length field unnecessary for IP version 6. The next is total length or payload length in IPv6. In IPv4, total length field represent the combined length of header and data. In contrast, IPv6 uses payload length field to indicate only the size of the data, as the header size is always fixed and does not need to be included in calculation. Identification, flags, and fragment offset. These fields are used for fragmentation in IPv4. In IPv6, the fragmentation header is not included in the main header, and it will not be used mostly since fragmentation is handled only at the source node and is not allowed by intermediate routers, and pass MTU discovery is used to avoid fragmentation by ensuring packet size appropriately for the entire path. Therefore, mostly fragmentation is not needed in IPv6, and because of that it is removed from the main header, but by necessity it will be added as extension header, which will be discussed shortly. The next is header checksum. In IPv6 header, the checksum is removed since it relies on error detection mechanism provided by higher layer protocols like TCP or UDP to ensure data integrity. And options. IPv4 options are part of the main header but are rarely used in practice. They allow for functionalities such as source routing and can extend the header length up to 60 bytes. Since these options must be processed by routers, they can impact the network performance and efficiency. In IPv6, the equivalent of IPv4 options are extension headers. Unlike IPv4 options, which are part of the main header, extension headers are separate and processed only when necessary. This design enhances flexibility and efficiency by keeping the primary header fixed. Shortly, we will provide an overview of IPv6 extension header. Now let's consider IPv6 header fields where only the name has changed while the functionality remains unchanged. Type of service, which is traffic class in IPv6. Despite the name changes, its functionality remains the same. It is used to classify different types of traffic and manage varying level of quality of service. The next field is time to leave, which is renamed to hop limit in IPv6. Both are used to limit the packet's lifetime. And the next is protocol, which is called in IPv6 next header, which is very important. In IPv4, it is called protocol, indicating the next level protocol, like TCP, UDP, and ICMP, which have in order the protocol numbers 6, 17, and 1. In IPv6, next header can be a higher layer protocol like IPv4 or an extension header. Shortly, we will provide an overview of IPv6 extension header. And only new field in IPv6 header with no equivalent in IPv4 header. It is specifically designed to work alongside traffic class field to classify traffic for quality of service process. To compare flow label with traffic class is used to classify different types of traffic such as voice, video, and data to apply different levels of quality of service based on these classification. For example, it can be used to ensure that video traffic gets higher priority than data traffic, or that voice traffic is handled with low latency. Flow label, on the other hand, is used to identify and manage packets that belong to the same flow. Within a single traffic class, the flow label can differentiate between different flow of the same traffic, the same type of traffic. For instance, within a traffic class designated to voice traffic, the flow label can be used to distinguish between different voice calls. This allows for potential quality of service variations and optimized handling for different voice calls or flows, even though they share the same traffic class. However, up to now, it is not implemented, but the header fields, it potentially exists in IPv6 header. Finally, what is particularly interesting about IPv6 header is that it has a fixed size, making it more efficient and requiring less processing time compared to IPv4 header. The efficiency is achieved because optional fields in IPv4 header have been restructured as extension header in IPv6 header. When optional information is needed, it is added as separate extension header with next header field pointing to it instead of directly to the upper layer protocol. Each extension header has its own next header field, which can either point to another extension header or to upper layer protocol. The other view of extension header in IPv6, in IPv4, protocol number point to the payload, but in IPv6 we have extension header, and each extension header next header can point to the next extension header, to the next extension header, to the next extension header, or to up layer protocol. I won't delve deeply into details of IPv6 extension header, but I will provide a brief overview of each one of the IPv6 extension header just for reference. I will give a quick definition of each header extension in the typical order that might appear in IPv6 packet. First, hop by hop options header carries optional information that must be processed by every node along the packet's path, such as collecting packet delay or throughput data. The next is routing header, specifies a list of intermediate nodes that the packet must be visit on its way to the destination, which is called source routing. And then fragmentation header handles packet fragmentation and reassembly. And then authentication header provides integrity and authentication for the packet, ensuring that the data has not been tampered with and is from a legitimate source. It is a protocol part of IPsec framework. And the next extension header is ESP, provides confidentiality or encryption as well as optional integrity and authentication. It is another IPsec protocol. And destination options header carries optional information that is processed only by destination node, such as mobile node's home address in IPv6 mobility. And the final header can be mobility header itself, which is not displayed in this image.